All right, so we're picking back up and now we're going to talk about electric current. So previously we talked about electric potential difference related with voltage. So that's that difference between one end of the conductor and the other. So one end has higher potential energy than the other, then the electricity will flow. Well, this is the flow. So electric current, or big I, is the rate of flow of charge through a cross section of a conductor in a unit of time. So electric potential difference, or the voltage, that is talking about the difference of the different potential energies. Electric current is talking about the flow that that potential difference creates. So big I is the quantity of charge over time. So basically how much charge is coming through. Without any voltage applied, the charged particles are going to move randomly through the material. So there's no current, there's no flow or direction because those guys are just going to kind of randomly run around on their own. But when you apply the voltage, then they'll all flow in one direction. Now, the rate of electric current is measured in amperes. So you've probably heard of this before. So the unit for current is amps. So 1 amp is 1 coulomb per second. So 1 amp is equal to 6.24 times 10 to the 18 electrons flowing past a point in, say, a wire in 1 second. So quite a few electrons moving past 1 point per second. So if you have a 4 amp wire, and actually that's how a lot of these are measured, a 4 amp wire will move how many coulombs? Well, a 4 amp wire has the ability to move 4 coulombs of electrons. And that's why it's rated as a 4 amp wire. It has the capability of moving 4 coulombs per second through any portion of the wire. So now we've got a little bit down on voltage, that electric potential difference, and now we've got current, the flow of those electric particles, or in our case, we're talking about electrons. So electric circuits, these are just a path for the electric current to flow through. So if there's nowhere for it to go, it's not going to be very helpful. So an electric circuit is this path for the electric current, but it has to contain some specific things at a minimum. So it has to have a device acting as an energy or a voltage source. So it needs to have something working as a voltage source. So this is generally either going to be a battery or some sort of electric generator. And so, for example, the plugs in your home, those are actually connected distantly to electric generators that are pretty far away, that are actually bringing that electricity to your home. You need something for the charges to do work on. So you're going to need some sort of light bulb, motor, a heat source or heating device like a heater, some sort of electrical device in the circuit for the charges to do some work. Otherwise, there's not much point in having an electrical circuit. You do need to have the wires. So the wires have to be able to connect the elements or there's nowhere for the current to flow. And then you can use switches, but they're not required. So you can just put an electric circuit together with the first 3 elements and be done. But without a switch, there's no easy way to turn off the thing that the charges are doing their work on. So you can't stop the light bulb, the motor, the heat, if you don't have a way to stop the current flow. You can, turn off the generator or pull out the battery, but it's easier if you put in a switch because a switch can be used to break the circuit path so that the electrons can't flow. That will stop the current and no longer supply the power on the circuit. So let's take a look at a circuit. So here we've got our voltage source, in this case, a battery. It is maintaining potential, a potential difference on the wire, because you've got a positive and a negative terminal. If you've ever looked at batteries, they've got a positive and a negative charge. And if you watched the batteries video, you saw basically how that works. You've got the high energy side of the battery and the lower energy side of the battery. The electrons want to go from the high to the low, and the circuit gives them the path to be able to do that. And so your voltage source is connected to the wires, and the wire is going to allow those electrons to flow. We have a voltage drop, a device for the electrons, the charges to do their work on, and then it will continue to flow to the other side of our voltage source. So that's that basic circuit. Now, like I said, we can put a switch in, and so generally we would want to put the switch in on this side, so we can put a break here. We could put a break here. It doesn't matter as long as the break breaks the circuit. So a switch, all it does is opens the wires so that they're no longer touching, and that keeps the electrons from being able to flow. And then when you turn the switch on, it puts those wires back together so that they're touching. So down here, this is just a picture to show you the same idea using a water wheel. So the pump is the battery, and so it pushes the water up and then back down so that it'll keep flowing, because we've got high levels of water here that will allow the water to keep pushing down because it's got higher potential energy. And then it pushes back down to the pump pumps it back up. All right, so our current, because we've been talking about current, it comes in two types. You've probably heard of AC current, DC current, which is funny because AC stands for alternating current, DC stands for direct current. So the C's are actually current. So what are these? So DC, direct current, the charges only flow in one direction. So if we have our circuit, so let me draw a little circuit here, and we put in our little battery, the charges are only going to flow this way, just like we saw before. So they only flow one way. This is what batteries do. So for example, batteries in flashlights, but also things like batteries in your laptop. So when you're using your laptop, your battery in your laptop is supplying your laptop with DC current. The plugs that you've got for it are actually taking AC current and converting it into DC current to charge your battery with. Alternating current, or AC current, is going to alternate back and forth. So it's going to switch directions back and forth, back and forth. And this is going to be done by a generator if we're talking about like electricity to your home, or an alternator if we're talking about electricity in your car. So these two are going to just flip that electrical current back and forth, back and forth. And so if we were to chart the electrical current, let me move my head out of the way. So you can see DC current stays steady because it's all flowing in one direction. But AC current, since it's alternating directions, if we were to follow it on, to graph it, it switches directions over time, and so it flips back and forth and has a frequency. In fact, in the United States, our frequency for AC power is 60 hertz, meaning that every 60 seconds it switches. And in other countries, that number is different. That's why when you go to other countries, you need to have different converters. It's not just because of the shape of the plug, but because they have different frequencies for their AC current. And our appliances aren't made to handle that. And so you need a converter to convert the AC current to our 60 hertz current in order for your appliance to be able to handle it. All of the electricity rules that you're going to see in future videos apply to both types of current, whether it's AC or DC current. So this video right here to explain the difference between AC and DC current will be posted if you want to see a little more in detail about how these guys are different and how they work in one of those circuits. Because you might be wondering, well, if AC current changes back and forth, why don't we notice it? And this video will cover that for you.